Alrighty, so today's lesson is going to be over chapter 24. It's called match pairs inference. So we're going to do a hypothesis test and a confidence interval on something called a match pairs. So again, make sure you download your notes and save them to your computer. Same thing with the PowerPoint. The PowerPoint is the insert key, and that's what we're going to use to make this video. So this is the PowerPoint, which you can find in Schoology. Okay, so chapter 24 is something called match pairs inference. Before we started, I need to remind you of like the vocabulary match pairs. So we did those last semester. In a match pairs experiment, there is, I guess, let me just read you the definition. It says, it is when an experimental unit, so either like people or pets or plants, whatever, experimental units with similar characteristics are paired together, and one person will receive one treatment, and then the other person receives the second treatment. That's called a match pairs. Or here's the more common match pairs that we use for, I guess, the AP exam. A more common match pairs is when the experimental units, so the people or the plants or whatever, they receive both treatments. So for example, like in a food tasting, like the person, like each person will taste like both cakes or both sodas or whatever they're testing. That's called a match pairs. Or when like the person will take both medicines, like they'll take like medicine A to see if it helps with headaches, wait a few weeks, and then they'll take medicine B and see if that helps with headaches, and then they compare which medicine is better. Or another example here is like when the student takes like both tests, so test A and test B, and see which test was easier, I guess. So that's the more common match pairs that we'll do in this class. It's called match pairs, and is when like an experimental unit receives both treatments. So that's the little review of the vocabulary word match pairs. So now let's determine whether this scenario is a match pairs or not. So it says a pharmaceutical company wants to test this new weight loss drug. Before giving the drug to a random sample, the company researchers take a weight measurement on each person. So that's like the first measurement. Every person's weight was recorded. And then it says, after a month using the drug, each person's weight is measured again. So this is an example where like each experimental unit tried both treatments. The first treatment was a placebo, like no drug. The second treatment was the drug. And now they want to know if there's a difference between using the drug and not using the drug. So this is what's called a match pairs. Each experimental unit, so each person, tried both treatments. And again, the both treatments were, the first treatment was placebo, like everybody's weight was recorded before using the drug. Then after a month on the drug, everybody's weight was recorded again. And you want to see if there's a difference in weight loss between using the drug and not using the drug. So that's called a match pairs. And today we're going to do examples like that. Here's another scenario. Let's see if this is match pairs. A researcher wants to know if a population of brown rats on one city has a greater mean length than a population in another city. She randomly selects rats from each of the cities and measures the lengths of their tails. So on this one, it doesn't really say that she's pairing the rats together. Here, it just seems like she's going to take one sample from city A and then a separate sample from city B. So this is just like two independent samples. So this scenario is not a match pairs. But the next one here, I think let's see this one. A researcher wants to know if a new vitamin supplement will make the tails of brown rats grow longer. I don't even know why we would do that, but anyway. She takes 50 rats and divides them into 25 pairs matched by gender and age. It literally says pairs, so match pairs. Within each pair, she randomly selects one rat to receive the new vitamin, and I guess the other rat doesn't. After 6 months, she measures the length of the tails. So this, like I said, it says literally matched pairs right there. So that's a matched pairs because the rats were paired together. One received the vitamin and the other one didn't. And that's a matched pairs situation. And I think last one here. Yeah, last one. A college wants to see if there's a difference in time it took last year's class to find a job after graduation and the time it took the class from 5 years ago to find a job after graduation. So researchers take a random sample from both of the classes, so last year's and the one from 5 years ago, and measures the number of days between graduation and their first day of employment. So in this kind of scenario, again, like they're not pairing any two people together, and it's not the same people. You don't have the same person doing both treatments. So this kind of situation or scenario would be two independent samples. So now that we've practiced a little bit about what's a match pairs and what's two independent samples, let's go ahead and do today's notes. So first of all, chapter 23, which you were supposed to do last week, that's called two independent samples. So make sure you do review the chapter 23 notes, the chapter 23 PowerPoint, and the video that I made. It's called chapter 23, two independent samples. So do that one and review it. Today, let's do chapter 24. Chapter 24 is called a match pairs. And I guess here goes the steps of a match pairs. I think everything is in your notes. Yeah, everything's on the notes written down so you can just read through it. So the steps of every hypothesis test is step 1, define the parameter. Here's the new parameter that you're going to do when something is a match pairs. You're still going to use mu because it's still your variable is still the mean, like the mean test grade or the mean weight. But now we use a little subscript d here for the difference. So mu, and here's how you would define it now. You'll just say the true mean difference in your match pair sample. And we'll try it today. The hypotheses, which are the second step of every hypothesis test, are going to be the null hypothesis should always have an equal sign. And this time you're going to use mu sub d equals. The alternatives could either be any one of these three symbols. You either put mu sub d is less than, or mu sub d is greater than, or finally mu sub d is not equal to. Those are the hypotheses that you'll use for chapter 24. Next, the conditions, they're pretty much the same as before, except for the very first one here. So if you recall chapter 23, when you're doing two samples, the condition should be like you have two independent samples or two independent random samples. This time, the first condition should be you have two samples that are paired. So the samples are paired, and they're supposed to be random. So samples are paired. Next, your paired samples have to be less than 10% of the population. And finally, for the large enough condition, the same thing as always, either the population of the pairs is known to be normal, or your paired samples are at least 30, or if you have a graph of your data, it looks symmetrical with no outliers. So if any of those three conditions are good, then that means your sample is large enough and you can go ahead and do the hypothesis test. So those are the conditions. Here's some formulas. This is and again, all of this is written in your notes. So this is the formula for a confidence interval of a matched pairs situation. The formula starts with x bar sub d plus or minus a t star. So it looks like we're going to be doing t intervals times the standard deviation of the sample divided by the square root of n. So that's one of the formulas that you'll need today. And for the hypothesis test, it looks like it's going to be a t-test. T equals, you'll take your x bar sub d minus the population mean divided by the standard deviation of the sample over the square root of n. So again, those are the formulas that we'll use today. And finally, I guess let's just do an example. Because after you find your test statistic and p-value, you're supposed to do your decision and conclusion. But let's just do it now. So let's try this. You'll need a calculator, or I guess you can just watch the video. Example 1. Having done poorly on their math final exams in June, 6 students repeat the course in summer school, and then they take another exam in August. If we consider these students to be representative of all students who might attend summer school, do these results provide evidence that the program is worthwhile? So basically it's just asking you, like, did the students do better on their test after summer school? And hopefully, yeah, they did. So I guess we'll just start our steps. Step 1 is supposed to be to define your parameter. Oh, so I guess obviously this would be a match pairs because that's what today's lesson is called, match pairs. But the reason that you know that example 1 is a match pairs is because here you have the data of the scores in June of 6 children. Then you have the data of the same kids, their scores in August. So because these results come from the same 6 kids, this is called a match pairs. Like every student's data was recorded in June, and then their same student's data was recorded in August. So that's called a match pairs. So we're gonna do a match pair test. Step 1, define the parameter. Here's how you start defining it. You start with mu sub d. Mu sub d equals the true mean difference, I guess, in their test scores. That's why you can define it. So true mean difference in scores. Perfect. So that's step 1. Mu sub d equals the true mean difference in their scores. Next, for the hypotheses. The null hypothesis, we assume there is no difference. So in the null hypothesis, we're supposed to assume that there is no difference in their scores. And therefore, if you were to subtract June minus August or August minus June, it doesn't matter which way, the difference should be 0. So that's going to be your null hypothesis, that the mean sub d or mu sub d equals 0. So again, we're assuming that they did the same, like their scores in August were the same as their scores in June. There was no improvement. And the way I subtracted August minus June. And because I subtracted August minus June, the alternative hypothesis would be, it's asking is the summer school program worthwhile? So basically it's asking is their score in August better or higher than their score in June? So if I were to subtract August minus June, I would want to have a positive difference. So I want to have my mu sub d, my difference, to be greater than 0, positive. Because that way, that means that their scores in August are higher than their scores in June. That gives you a positive number. So you would write that as your hypotheses. So step 1 is done. I define the parameter. Step 2 is done. I wrote the hypotheses. Step 3, we're supposed to write some conditions. So assume our samples are paired and they are a random sample So again, here's your samples. You have two samples, the one in June and then the one in August. But we're assuming that they are paired together because they come from the same student. And we're just going to assume that they're random. And it says here, representative of all students. So that's fine. So I'm just going to put, you can just put like, assume the two samples are paired and that they are a random sample from the population. I wrote, the samples are from the same student, so they are paired. And we will assume that these 6 sample differences are a random sample of the population. Most of these you'll see as multiple choice on your testing quiz, so just select the one that sounds the same. So again, your samples are paired, and we're assuming they're a random sample from the population. Next, assume that your samples are less than 10% of the population. So surely, like 6 students is less than 10% of those who take summer school. So you can just put like the sample of 6 students is less than 10% of those who are going to take summer school. Or you can put what I wrote there. And then finally, for the large enough, remember that for the large enough, either the problem says that the population is normal, which in example 1, it doesn't say so, or your sample is at least 30, which in this case, both of the samples are only size 6. So that's not at least 30. So then the last option, which is what we're going to have to do, is we're going to have to take those samples and graph them to see if they look symmetrical with no outliers. So that's what I'm going to do. And I need to show you how to do that. Okay, so basically, okay, let me get the calculator. Okay, first of all, here's what we need to do. We need to take these 2 samples and combine them into one single sample here. So I'm just, so here, difference. Okay, so we need to take these 2 samples and combine them into one single sample by like literally taking the difference between August and June. So we can do it by hand, or the calculator will do it for us in a minute. Like we're gonna have to take their August scores and subtract the June scores. So we're gonna take, for example, 50 minus 54. Well, that kid didn't do better. His difference is a -4. And then so on. We need to take 65 minus 49 and see that difference. So he did better. And this one, 75 minus 68. But let's just go ahead and let the calculator do this for us. So again, we're combining both of the samples into one single sample of differences. And that's how we're going to do our hypothesis test, with one single sample of differences. So let me show you. On your calculators, we're going to have to type in the data into a spreadsheet. So go to the Excel group looking Excel sheet. For starters, go ahead and type in the June scores, 54, 9, 68, 66. And then type in the August scores, 50, 55, 25. And then I always like to label them. So let's just go with X and Y. So X was June, Y was August, and then here's what we're going to do on the next column. I'm going to call it D because that's my variable, like my difference, D. And instead of like you individually subtracting 50 minus 54 and 65 minus 49 and 75 minus 68, what you can do is like an Excel document right here below in this specific column here, you can put equals. And remember that I'm going to subtract August minus June, so Y minus X. Press that, enter. It's going to ask you for a column reference or variable. You want to switch to variable. So Y is a variable, X is a variable. And now the calculator has subtracted the August scores minus the June scores for every child. So these are their differences. And it's not required for you to write them, but I'm just going to write them right here. So -4 was one of them, 16, 7, -2, 6, and then there was one more, 10. Oh, yeah. So in conclusion, here's what I've done. I have taken my two samples that were paired together and I made them into one single sample of differences. So now what I'm going to do is I'm going to do my match pair test by just doing a one sample t-test. So this just becomes a one sample t-test. Or can't type. Okay. So that's what the match pairs is. It is a special type of one sample t-test. So again, a match pair, because on your calculator, you're not going to find something called match pairs. You just need to know that a match pairs is a special type of one sample t-test. So that's what we're going to find on our calculator, one sample t-test. So let's do it. And I still need to graph this data, so let me graph it. So I'm still need to see if the data looks symmetrical. And by the data, I mean like my differences here, like -4, 16, 7. So I want to graph variable D. So the way you make a graph, remember, is like doc47, doc, insert, data and statistics. Why didn't you do it? Oh, there it is. Click on the x-axis, and remember, you want to add the variable D, like the differences. So one more time. From the spreadsheet, you press doc, insert, data and statistics. You click on the x-axis to add the D variable of differences. Now you want to change this to a either histogram or box plot. So I think you go to menu, plot type. Wait a second. Okay, go to menu, plot type, box plot. Okay, totally not symmetric, but we're just gonna do it anyway. So this is your data. It looks skewed, but we're still gonna do the test. So the data looks skewed. So I guess I made up these numbers myself, so I didn't pick a good example. We're just not gonna waste it. We're gonna do it anyway. So the data looks slightly skewed, but Mrs. Garcia says do the test anyway. So over here on my conditions, it says the box plot shows no outliers, although it does appear to be skewed. However, we're just gonna do the problem anyway. So there it is. I sketched a picture. I mentioned that it does look skewed, but we're gonna do the test anyway. So the way you would do your test now is, like I said, on your calculator, it's called a one sample t-test. This is the formula for a t-test, or specifically like a match pairs t-test. We're going to need the sample mean minus the population mean divided by the sample standard deviation over the square root of n. So I already know the answers because obviously I did this before, but here's how you get all these numbers. The sample mean is going to come from your calculator. So on your calculator, you have to go back to a spreadsheet and you need to find a t-test. So like I said, there's no match pair test. It's just a special type of t-test. So go back to the spreadsheet and do menu, statistics, stat test, and it's the second one, t-test. It's just called a t-test. T-test. And this time, leave it as data because you do have the data in the spreadsheet. So leave it as data. And then it's going to ask you, like, what is the population of differences? And remember, we assume it's 0 because we assume that the students didn't do any better in August. And then it's going to ask you, like, where do you have your list? Remember, I called it D. Without the little brackets, make sure you just put like a letter D. Frequency, leave it as 1. And then the alternative, it depends on which way you subtracted, but we did August minus June. So we want to know if the difference is positive. So do mu is greater than. And after that, just leave everything else as is and press OK. So here's everything you'll need. You'll have your test statistic, 1.8. You'll need that for sure. It'll be fill in the blank on your test or quiz. Next, you'll have the p-value. Again, another fill in the blank, p-values. This is the p-value that we'll use to make your decision and your conclusion. But then if you keep scrolling down, you'll have the degrees of freedom, which is sample size -1. Okay, if you keep scrolling down, this is the sample mean. So that is the mean difference between those samples. So that's the mean of the differences, 5.5. Scroll down one more time, and then this is the sample standard deviation, 7.47. So that's where I got these numbers from. 5.5 was the sample mean, minus 0, which is we assuming that there is no difference, divided by 7.48, which was the sample standard deviation right here, 7.48. And now I can just copy that. That's going to equal to 1.80. So that equals to 1.80. And that is how you calculate your test statistic using the calculator for a match pairs test / one sample t-test. Next, you need to practice getting the p-value. Okay, first of all, we already know the p-value. You can copy it, 0.0657. So there it is, 0.0657. Technically, I guess I didn't even show my work here, but I just copied it, 0.066. Technically, you need to remember how to do those because I think they were on your chapter 22 quiz and they'll show up again on your next quiz. But the way I would get this 0.066 is by doing a TCDF. So on your calculators, you should be doing like a TCDF of more than 1.8, so 1.8 to infinity. And then don't forget to use the 5 degrees of freedom. And that's going to give you your p-value, which you can copy straight from the calculator. And after that, the decisions and conclusions are always the same. So that p-value is a little bit large, or it's for sure more than 5. So you can say that p-value is more than 5. So I failed to reject the null hypothesis.
Where did you get the 1.8
from? The 1.8, for starters, I copied it from the calculator right here where it says T, 1.8. But technically, it came from doing 5.5 minus 0 divided by the standard deviation over the square root of 6. So with that large p-value, I failed to reject the null hypothesis, and there isn't enough evidence that students are doing better after summer school. So I guess summer school was not worth it. On average, I guess. There's not enough evidence to suggest that the program is worthwhile. So I guess the kids just don't care about summer school anyway. And that is how you do a hypothesis test. I'll pause for questions, and then we can do the interval. Pause for questions.
What commands are you putting in the calculator? Like in order, because.
Okay, so now that you've done the match pairs test, which is a one sample t-test, now let's do a letter B, calculate and interpret a confidence interval. So again, the confidence interval is just going to be a one sample t interval, or just call it t interval. This is a formula. It's supposed to have like the little subscript d here, but it really doesn't matter because it's the same formula. So for this, again, if you show your work, you will show the sample mean was 5.5 plus or minus, you want 90% confidence. So I'm doing inverse t of 0.95, which requires a degrees of freedom. So 6 minus 1 is 5 times the standard deviation, which was the 7.48 over the square root of 6. So that's how you would show your work. But let's just use the calculator to get the answer. So again, on your spreadsheet, Just find something that's find an area that is blank. So I'm over here like in column H. Okay. So let's do a T interval. So on the spreadsheet, menu, statistics. This time we're doing interval, and is the T interval. So we're going to do letter B. Menu, statistics, intervals, T interval. Leave the data as data. And now, I think I switched the name to E. I feel like I switched it to E because, I don't know, let's go with it. So I think I whatever you called it, it should have been D, but I think I switched my name to D when I paused the video. Frequency, leave it as 1. Confidence level, 90%. And then you can just, the results can be stored anywhere. That's fine. And here it is. It's giving you the lower bound and the upper bound. So that would be your interval that you would copy. Negative 0.65 to positive 11.65. Negative 0.65, positive 11.65. That's called an interval. And you always interpret it with a wording recipe. We are 95% or we're 90% confident that, I just put mu, but technically that the mean difference lies between negative 0.65 and 11.65. You can copy that. And then final question on example 1 is always going to ask you, would you reach the same decision and conclusion using your interval as you did with your hypothesis test? And like I told you before, the answer should always be yes. If you did it right, yes, the decision and conclusion should be the same. So in this interval here, because 0 is contained in the interval, which is the null hypothesis, so because the null hypothesis of 0 is contained in this interval, I do not reject the null hypothesis, or I fail to reject the null and conclude that we don't have enough evidence for the alternative to be true. Or in other words, same decision and conclusion as before. Now that's how you do a match pairs test and a match pairs interval, which basically is just a 1 sample t test and a 1 sample t interval. So pause the video for questions. Okay, last thing for chapters 22, 23, and 24. You need to be able to read a, it's called a computer printout, or like a little chart table looking thing. So here it is. On the back of today's notes, example 2. You are given some scenario with this little computer printout, and you need to know where to find some information. So I guess first of all, let me just read it. We wish to determine if students at Clemens High School log into Skyward to check their grades more often than students at Travis High School. Oh, so basically, as a teacher, I can see how many times you guys have logged into Skyward, like so far. So sometimes just for fun, I just start calling people. Like some people like 8,000 times. So like, I don't know, like 100 times a day. Or like some people 5 times or 400 times or 300 times that you've logged into Skyward. I can see how many times you've done that this year. So after this, we can play that game. I'll start calling all yours how many times you've logged in. But anyway, so I can see that on my Skyward. So apparently we collected data from 30 randomly selected students at each of the schools and recorded the number of times that they logged into Skyward. The following output was recorded. So it says, assume that CHS was sample 1 and Travis High School was sample 2. So here's a bunch of stuff. And now here's what you'll need. You'll need to find, first of all, okay, so let's just answer letter A. It says, letter A, like what would be the null and alternative hypothesis for this situation? And remember, the situation is we want to know if students at Clemens High School log into Skyward more than students at Travis High School. So we want to know if sample 1 is more than sample 2. So here where it says hypotheses, it's not going to be A or B because those are not parameters. Your hypothesis should have the mu symbol and not the X bar. So it's not A or B. not E either, because remember for the null hypothesis, then it should have an equal sign. So it's either C or D. And it's probably D because we want to know Clemens is more than Travis, so mu1 minus mu2 is greater than 0. So letter A is D. So that you'll need. Circle it, D. Next, now here's what you'll need to chart. You need to find the test statistic and the p-value. So let me find you where the test statistics are. The column that says T, that is your test statistic / t-score. And we should always be looking at that row that says unequal on it, like the top, I guess this first row. We never look at the row that says equal. That would be something else, even though here it looks like they're the same value. But anyway, go ahead and always find the t-score on the row that says unequal and the column that says t. So 2.27, 2.2745 is your test statistic. And it will be a t-score because because for 2 samples, it's always a t-score anyway. And then finally, here's what you'll need, the p-value. Again, the p-value is the one that says on the unequal row, but this time the one that says probability is greater than. Now you have to be careful with the p-value because p-value is always a 2-sided p-value. So notice how it has like the little absolute value of t right there. So that means that this p-value is for the greater than and the less than condition or hypothesis, I guess. So because it is a 2-sided p-value, sometimes that'll be the answer. Like if you were testing to see if your alternative hypothesis was a not equal to symbol, then that would be the correct p-value. But because on this example, we wanted to know if Clemens students log in more often than Travis students, we're only going for a 1-sided p-value. So that means that we're going to have to take that p-value and divide it by 2. So there's my answer, D. And like I said, I forgot to circle letter A, but that should also be D. And so that's how you read a chart. And then finally, you have to go and do it backwards. So the last example 3. And by backwards, I mean on example 3, you're given the p-value and you need to try to find the test statistic. So let me show you how to do that. You'll need a calculator. I guess I'll read the scenario. It's example 3. Different varieties of fruits and vegetables have different amount of nutrients. These differences are important when the products are used to make baby food. We wish to compare the carbohydrate content of 2 varieties of peaches. The data is shown below. So here's some data. It's giving you a 2-sided p-value. So here it is. And now letter A, letter A. We wish to determine if the 2 varieties are significantly different. So here your alternative hypothesis would just be different, would just be not equal to. So your alternative hypothesis is a 2-sided hypothesis. So I'm going to leave the p-value as is. So you don't have to divide it by 2. You can just leave it as is. So that is my p-value right there, 0.2039. And finally, you have to work backwards, like use this p-value to give me the test statistic that goes with it. And okay, I didn't show my work, so I have to show you my work. The way I did this one was probably is best if I draw a picture. So let me wake up the camera so I can draw a picture of my work. So I'm trying to show you how to get the test statistic based on this p-value. Here's how you'll do it. Okay, so waking up the camera. Okay, so p-value. So we just figure out the p-value was 0.0. No, what was the p-value? 0.2039. So here's how you find that test statistic for this one. It helps if you draw a normal curve. And then, so this is a 2-sided p-value. So that means like the area on the top tail plus the area on the bottom tail equals to 0.2039. So first of all, I need to know what is this t-score and then this negative t-score. So the way you would do it is I'm going to take the 0.2039 and I'm going to divide it by 2 first so I can see what's the area on each tail. Divided by 2. So that means that this area here is 0.10195. It's the same thing with this area. So let's find the lower one first because it's going to be easiest. So to find this t-score here, and you don't have to call it negative, it's going to automatically come out to be negative. But the way you find this t-score is with an inverse t of this area, 0.10195. And then you need some degrees of freedom, which I'm sure in the problem somewhere. 10. It's on the chart, 10. So if you do that, that's going to give you one of the t-scores. So that's giving me the negative one. 9. Okay. So that's this negative t-score. And then the other one, the positive t-score, is just the same thing. It's just going to be positive. So positive 1.359. And that's why I put here for my t-score. We don't know exactly which one it is because the hypothesis was just a not equal to symbol. So it could have been the positive 1.3 or the negative 1.3, either one, or plus or minus. So now that's everything you'll need. Practice, like there's a little practice on the bottom of this page. Practice that and just practice chapter 24 specifically, but review chapters 22, 23, and 24, which are all the hypothesis for means. Stopping the video.